field for ages, and the people who also represent and glorify Indian solar physics on the world stage. Friends, today's lecture, we have with us two such renowned big names in solar physics in India, Professor Arnab Choudhuri, who is an astrophysicist and professor at Department of Physics, Indian Institute of Science, Bangalore. And today Professor Arnab Choudhuri will be chairing the session to today's program. And the talk will be delivered by astrophysicist Professor Dipankar Banerjee, who is currently the director of Aryabhatta Research Institute for Observational Sciences, ARIES, Nainital. Dr. Banerjee's area of interest is the sun and the solar atmosphere. His work has enriched our understanding of the sun and its impact on space weather. Warm welcome to you, sir, to both of you. And to begin with, I request Dr. Nakul Parashar, Director Vigyan Prasar, to deliver the welcome address, with whose motivation and leadership Vigyan Prasar, we have been able to take forward the legacy of science communication across the country and also at the international platform. Before I invite Dr. Parashar, I would like to remind the audience to mute their microphones for avoiding any disturbances during the session. And also I would like to encourage the audience to avail this golden opportunity to interact directly with the speakers, the well-known physicists, as well as after the talk. And you can directly ask questions on the Zoom platform, on this platform, online platform. And this program is also being live streamed on YouTube channel of Vigyan Prasar and ISTI Portal. So the queries that we will be receiving on these two platforms will be taken up by our online moderators, Dr. Neetu Srivastava and Ms. Tusha Agarwal, and we will pass on them to the speaker and the chairperson. And thank you so much for being with us today. And we invite you for your live interaction. Sir, Dr. Parashar, I invite you for your welcome address. Over to you, sir. Thank you.
Namaskar. Thank you, Dr. Kinkini. It's indeed a great pleasure, honor for me to welcome Professor Arnab Choudhuri and Professor Dipankar Banerjee. It gives me goosebumps when I feel that I'm here sharing the dais with you. It's always been, a dream to be around with people who've been working so deep and have such a long history and such a wide experience in the area of astrophysics. Something that when I opted, I had no other option but to go for material sciences as a part of my physics. But always looked at the stars and wondered if I could ever get deeper into it. Anyway, but it's always a pleasure to find, an opportunity to do this. And fortunately, Vigyan Prasar has been associated with RIS in organizing the STIP lectures. And I would want to, tell Professor Arnab and Professor Dipankar about the STIP lecture series that has top people in their area domain that have delivered these lectures. And we feel very honored, privileged to have both of you with us today. Thank you so much for having accepted our invitation for this lecture. And I'm sure there's a lot more that we could go on. And please forgive me, I've been a teacher at the College of Engineering, so I normally don't stop till my 40 minutes are over, but I'm sure I don't have that privilege here. So I would now request Professor Arnab to take it over from here and go ahead, because all of us are anxiously waiting to listen to both of you, and particularly Professor Dipankar Banerjee on this interesting topic that we have chosen today. So thank you so much on behalf of Vigyan Prasar, RIS, and all other organizations that are working with us to organize this monthly lectures that have brought a lot of information and a huge repository of knowledge that has gone in. Thank you so much. Jai Hind and Jai Bharat.
To you, Professor Choudhuri, yes.
Okay, so thank you. Can you hear me now?
Yes.
Yeah. So thank you so much, Dr. Parashar and Dr. Mishra. So let me share my slides. I have only a very few slides. So you can see my slides?
Yeah.
Okay. So I am extremely happy that Vigyan Prasar is organizing this public lecture on solar physics in India to be delivered by Professor Dipankar Banerjee. It is my honor and privilege to chair this lecture. And I have been asked to make a few preliminary remarks to set the stage for Dipankar. So let me begin with the assertion that solar physics is one of the most thriving areas of astrophysics in present-day India. To support this assertion, let me just mention two facts. So this Astronomical Society of India started giving Modali Award 3 years ago for an astrophysicist younger than 45. And out of these 3 Modali Awards which had been given so far, 2 went to solar physicists. And again, secondly, this International Astronomical Union also 3 years ago started giving a PhD at large award for the best PhD thesis in astrophysics from any country in the world. But very, very remarkably, out of these 3 PhD at large awards which have been so far given by International Astronomical Union, 2 have come to India, to Indian students who had done their PhD thesis on solar physics. So I think just these 2 facts will convince you of my assertion. And on a personal note, this first winner of Modali Award and the first winner of PhD at large award both happen to be my former PhD students. So anyway, it is often said that we study astrophysics only out of intellectual curiosity, and it has no connection with our everyday life. However, solar physics is one branch of astrophysics in which deal with phenomena like solar flares, which do affect our everyday life, as surely Dipankar is going to explain in a few minutes. But in spite of that, the general public do not know as much about solar physics as cosmology or black holes. So perhaps we solar physicists are also at fault that we do not publicize our field properly. So since Dipankar will mainly talk about what is happening in solar physics in India in the last few decades, to set the stage, let me tell you a little bit about the historical growth of this field, both in the world and in India. So we often say that modern astronomy began when Galileo turned his telescope towards the sky. And one of the objects which Galileo studied was the sun. So he noticed that sunspots, these dark spots on the surface of the sun, they keep changing their positions from day to day, from which he concluded that the sun is rotating about its axis. So this discovery of solar rotation by Galileo can be taken as the beginning of solar physics. Then in the year 1844, Schwabe discovered that sunspots have a 11-year sunspot cycle. In other words, the number of sunspots seen on the sun, that the number goes up and down in a cyclic fashion with an approximate cycle of 11 years. And then in 1859, Carrington became the first human being to observe an explosion on the sun, a solar flares. And how these things like sunspots, their cycle and flare, how these are produced, a definitive clue for that came in the year 1908, when Hell discovered that sunspots are regions of very strong magnetic field, about 5,000 times stronger than the magnetic field at the geomagnetic poles. So now we know that the 11-year sunspot cycle is the magnetic cycle of the sun, and this magnetic field plays the crucial role in the formation of sunspots and the production of flares. And now the sun happens to be a body made of a plasma, often called a fourth state of matter, a very hot gas in which atoms are broken into positively charged ions and negatively charged electrons. So to understand various solar phenomena, we need to know how to handle this interaction of plasma with the magnetic field. So these basics of the subject, magnetohydrodynamics, they were laid down in 1930s and 40s by such scientists as Alven and Cowling. And after laying down of these foundations from 1950s, a really glorious era of solar physics began with two landmark papers by Eugene Parker. So in 1955, he formulated what is called dynamo theory, which provides the explanation of how magnetic fields arise in astronomical systems. And then in 1958, he theoretically predicted that there will be a flow of plasma starting from the sun and flowing through the entire solar system, which he called solar wind. Till that time, it was thought that the space around the Earth is completely empty. We now know that the Earth is the solar system is embedded in the solar wind. And some 4 or 5 years after the theoretical prediction, the solar wind was discovered from a space mission. And from 1970s, there have been regular space missions dedicated for studying the sun, as Dipankar will discuss. So after telling us how this solar physics developed in the internationally at least till the middle of 20th century. So let me say a few words about India. The first large modern astronomical observatory in India was a solar observatory which was set up in Kodaikanal. And then in the first decades of first few years of 20th century, some important developments took place. In 1909, Evershed, who was director of the Kodaikanal Observatory, from there discovered a kind of flow pattern around sunspots, which is called Evershed effect. And then in 1920, Meghnad Shah formulated the theory of thermal ionization by applying it to the sun. So the first paper of his on this subject was titled Ionization in the Solar Chromosphere. But after this glorious beginning, for several reasons, there was a lull in solar physics research in India for several decades. And then it got revived only in 1970s and 80s due to some scientific leaders like Bhatnagar, Chitre, Hassan, Venkatakrishnan, Dwivedi, and many others. So Dipankar will be talking about this era. So let me just mention that some of these pioneers in solar physics in India had also been interested in science outreach. So I still remember a fantastic public lecture on the sun given by Professor Arvind Bhatnagar shortly before his untimely death. And then Professor Dwivedi wrote a superb article on solar corona, which appeared in Scientific American and was in fact selected as a cover article of Scientific American, a very rare honor. And I also have tried to do my little bit that I wrote a popular science book, Nature's Third Cycle, a story of sunspots, published by Oxford University Press. And if you don't want to read the whole book, but want to have a summary of that, then you can listen to my lecture, which is available on YouTube here. So this was the very prestigious TIFR Science Day lecture, which I was invited to give. So before giving the floor to Dipankar, so let me just end by raising one provocative question, which Dipankar may address, that in the last few decades, there has been an explosive growth of solar physics in India. But still, is that enough? So we often like to compare India with China. So since I know about the solar physics in China quite well. So let me make a few remarks about that. So India was definitely ahead of China in solar physics when I was requested to supervise a Chinese student, Ji Jiang, in 2006. So during a brainstorming session of Chinese Academy of Sciences, it was concluded that that China it was noted that China has no expertise in solar dynamo theory, and it was desirable that a young Chinese student should get into this field. So from the Chinese Academy, I received this invitation to come as a visiting professor to Beijing for a few months. Then Ji also came to India a couple of times. And in fact, she had the benefit of attending a superb solar physics school organized by Dipankar Banerjee in Kodaikanal Observatory. So here you can see me standing in front of the historical telescope of Kodaikanal Observatory. This is Ji and my other student Piali Chatterjee, and three of us developed theoretical formalism to predict the strength of a solar sunspot cycle before its advent. So we felt honored that our paper was selected as editor's choice selection in physical review letters as indicated by this sign, which is a great honor for a physics paper. But more importantly, after 4 or 5 years later, when the solar cycle reached its peak, its strength was found to be exactly as what we predicted. So in the history of our field, this is the first time it was possible to predict the strength of a solar cycle successfully before its onset. And coming to the question, is India still ahead of China in solar physics? My answer is probably not, though China is marching ahead very fast. So though we have made quite a lot of progress, we need to do more, as Dipankar will surely point out. So now coming to Professor Dipankar Banerjee, his early education was in Kolkata, BSc from St. Xavier's College and MSc from Calcutta University. Then he came to do PhD from Indian Institute of Astrophysics under the supervision of Professor Siraj Hassan. And in fact, he also interacted with me especially when Professor Hassan was away for a sabbatical leave. And the first paper of his life was written with me. And then he went for postdoctoral work to Armagh Observatory in Ireland and Leuven University in Belgium. And then he, in 2004, he again joined the faculty of Indian Institute of Astrophysics. And then 2019, he became the director of ARIES. And he's an elected fellow of Indian Academy of Sciences and National Academy of Sciences in India. And I would say that he's a very versatile solar physicist who has worked in theory, data analysis, instrumentation. So one can hardly find another person in India more qualified to talk about solar physics in India. So Dipankar, the floor is over to you. And let me try to stop sharing the screen. Yeah.
Let me start sharing it and ensure that all of you are able to see my screen. Is
Yes,
my
sir.
screen? Yeah.
Yes.
Thank you very much first to Vigyan, Prasar, Dr. Kinkini and Dr. Nakul for giving me this opportunity. And thank you to Arnab. We fondly refer him as Arnab. I must say, this kind of platform is used for motivating youngsters. And I have to agree that my journey into solar physics was motivated by Professor Choudhuri Arnab as a lecturer in industrial science. And I'm really, privileged today to be introduced by him. And I also noticed that there are quite a few senior members from the solar physics. Professor Antya is online, Professor Ananth Krishnan is there. It's a real honor for me to speak in front of them, though virtually. So let me start my journey. So what I propose today is I probably will not be able to do a full justice of describing what all things happened over several decades, I will try to connect some of the older observations and where we are heading for. Because I see that in the current epoch, we are really heading into a probably golden era of solar physics, at least in the observational sciences. And I will also mention that today I'm going to probably focus primarily on the observational sciences and the prospects what we have, and connect with the bit of history. But I have to be a sort of excuse that I will not be able to do a proper justice of really be able to cover the really history of solar physics in India. In half an hour, that will not be a right thing to do. So I decided that I will sort of only connect. And why do we need, first of all, to study the sun? That also has to be, briefly mentioned here. So here I am. I'm actually situated at the Nainital, and I'm going to talk, actually delivering this lecture from this building right now. This is called Aryabhatta Research Institute of Observational Sciences. This is our older campus at Manora Peak, but we have a new campus which proudly hosts the largest optical and infrared telescope from this part of the globe, namely the Devasthal Optical Telescope, which you see here. I will not be talking about these facilities, maybe some other opportunity. I'll be focusing on our nearest star, the sun. I'm currently at ARIES, but I'm still, a proud member of Indian Institute of Astrophysics, and I also affiliated member of Center for Space Sciences in IISc, Kolkata. Very briefly, the solar facilities, historically, it has been mentioned in the introduction session by Dr. Kinkini. We have a H-alpha telescope at Nainital, which looks at solar flares primarily. These are explosive, phenomena happening in the solar atmosphere, which affects our interplanetary space, and eventually it also affects our near-Earth environment as well. More recently, Udaipur Solar Observatory has been expanded with a new facility. This is a beautiful, observatory on the lake. I will show you one or two more figures. Kodaikanal Solar Observatory is one of the oldest observatories in this country, and Dr. Kinkini has mentioned its legacy as well. I will connect that as well. There are also few solar radio facilities, and I will come back to this particular aspect that the modern day astronomy demands multi-wavelength. And what are the advantages of doing multi-wavelength that I will also describe. And in that context, solar physics is actually paving a good way. This is a fantastic, radio facility. Of course, this is not dedicated for solar observations, but primarily for distant objects. But it does have a solar mode of observation possible as well. We have near Bangalore a radio heliograph, which is operated by Indian Institute of Astrophysics again, which again looks at the radio wavelength to study the sun. And of course, good old UTI radio telescope is also there, which is operated by TIFR and NCRA, which also looks at the sun. So these are existing solar facilities from the ground. And as I mentioned already, the Kodaikanal Solar Observatory of the Indian Institute of Astrophysics is located in the beautiful Palani range of hills in southern India. It was established in 1899 as a solar physics observatory, and all the activities of the Madras Observatory were shifted to the Kodaikanal. Dr. Kinkini mentioned about it. And this is the oldest observing facility. Still, there is a small little telescope here, which looks at the sun and every day takes one image from the oldest telescope, probably this part of the globe. It also has one of the oldest library. It has more modern facilities in terms of a twin telescope, which looks at the sun with two different wavelengths. It has this solar tunnel tower. You could see this is actually showing a lot of these domes, because underneath there is a tunnel. The sun light is ducted through this telescope dome into the tunnel, and it does a lot of spectroscopy and so on. More recently, there has been a new telescope, H-alpha telescope, looking at the flares and dynamic activities on the solar atmosphere. And there are also other facilities where you can direct the sunlight through a combination of mirrors into a room, and then more sophisticated optical experiments can be done in this kind of facility. So Kodaikanal Observatory, although this is a very old observatory. It continues its older operations, and also it has have modernized with a certain modest observational facility. It's not the cutting edge. We are aiming for the best next generation telescope. I will talk about it, but it still continues to do some observations of the sun on a daily basis from Kodaikanal. This is more of a modern solar observatory, probably now the largest solar facility from the ground base at Udaipur in this beautiful lake. There is a multi-application solar telescope. It is a 0.5 meter, telescope which has a good, feasibilities of measuring the magnetic field on the sun. As Professor Choudhuri mentioned, that we know that the sun is our nearest star, and it is a dynamic star. It changes at different time scales. And now we understand that all the time scale variations, what we see is primarily because of the variation of its magnetic field's presence or absence. And this is how we, different, measurements of the magnetic field with the highest possible resolutions and accuracies are at the demand of the hour. So most of the ground-based facilities are dedicated for these kind of magnetic field measurements. I will not get into technical details, but if some people have questions later on, we can try to address. Essentially, we are looking at sophisticated magnetic field measurements through its polarization properties or magnetic other properties. Now let me get into briefly, why do we need to study the sun? Sun is our nearest star. It's a normal star. It's a middle-aged star. We call it main sequence of spectral type. Do not have to worry about really this jargon, but you can just think about any star is born from an interstellar medium, then it undergoes its evolution like our life cycle. Probably I'm crossing my middle age. So sun is still in this middle age, and it will go old, and eventually it will have its own death. But we don't have to worry about these time scales of millions of years, and we are happily sitting in its middle age. Sun is a spatial star because it is the only star on which we can resolve the spatial scales on which the fundamental processes takes place. This is actually a very important statement, because majority of the object in the sky, what we study them or what we observe them is as a point object. We really cannot see such details on the surface of that particular object. Whereas sun being close to us, with the advent of the modern telescope from ground and space, we are able to see much more details. And that particular details we extrapolate to other astrophysical objects. Of course, sun is a spatial star because it provides almost all the energy to the Earth. Our existence is because of the sun at an appropriate distance. So we should be, worried about, we may do a Surya Namaskar in the morning or not, but we have to realize that our existence is because of the, of the presence of this nearest star, sun, at an appropriate distance away from us. From a physics point of view, it is also a special star because it provides us with a unique laboratory in which to learn various branches of physics. Professor Choudhuri mentioned in his opening remarks that we have this fourth state of matter, primarily the plasma physics. In the universe, actually 99.9% of the universe is actually in the plasma state. So if you really want to study the properties of matter in the different astrophysical scenario, you need to take plasma physics domain, and sun provides us with a unique laboratory, because some of these experiments actually we cannot conduct in the terrestrial environment. So that's the limitation of a terrestrial laboratory as well. As I mentioned briefly, the sun varies with time. Sun's behavior varies with time, and primarily we understand that the sun, like all stars, is a very dynamic star, always active, always changing. And more we learn about our own star, the sun, we will be able to understand the other astrophysical objects much better. So that's the point. And for the physics students, you name any branch of physics, whether it is atomic physics, particle physics, nuclear physics, spectroscopy, plasma physics, we have an application in the sun. So that is why, I came from a physics background, and I didn't have any knowledge, about any astronomy when I came for my PhD, and I chose solar physics because I felt that my classical physics background will be probably more suitable for the study of the sun. here I show a actually movie of the solar atmosphere. This is taken from a NASA satellite called Solar Dynamic Observatory. It is looking at the outer atmosphere of the sun, namely the lower corona. And what you see here, there are the certain regions in the sun which are bright. And in those regions, we also see there are certain kind of structures. These are called loop-like structures, where we understand now all these structures are governed by the presence of the magnetic field. They are actually all associated, these regions are all associated with a sunspot. And as Professor Choudhuri mentioned, sunspots are the dark regions on the visible surface of the sun. Historically, Galileo started saying that. I will show you that. And then these regions are called active region. And you could see how active it can be. The amount of material which is exploding out of this region is going to travel to the interplanetary space and may head towards us as well. And it can interact with our satellite, it can interact with the people who are walking in the space, or it can interact with us as well. But fortunately, Earth has its own magnetic field, and it provides a shield for these kind of material and the energetic particles and magnetic particles and all that which are coming to reach us. So if Earth would not have its own magnetic field, we would have been in great danger. Probably our existence would not have even happened. So here you see that these are called the active regions, and the other regions where are that kind of dynamics you are not able to see from small observations. They are in the past they have been named as quiet region, but I will show you that there is nothing quiet actually in the sun. Sun undergoes all kinds of temporal changes in different parts. The scales of the changes could be different, but they are dynamic all the time. So there are variability in terms of seconds, minutes, hours, days, months, years, and millennia. So we need to really understand these variability in a much more greater detail, and with probably different scales of applications in the physics as well. This is what Professor Choudhuri mentioned in his first thing. Galileo actually probably gave this first thing of modern astronomy, and along with the solar physics development as well. So this is actually an animation showing Galileo's hand-drawn locations of the sunspots. So he identified them. Of course, he didn't know at this point that the sunspots are probably strong concentrated magnetic field regions, but he identified them, and then he noticed that in subsequent days these objects are actually moving towards the right. So this is again an animation in a slightly bigger scale. So Galileo noticed already that sunspots move across the solar disk in accordance with the rotation of a round body. So it can only happen if some object is rotating around its own axis. So this is again, you can see that more than 400 years back, what kind of inputs we already had. Now today, if you look at someday towards the sun, it may look very boring because it doesn't have any special features. But some days you will find there are these objects, these are sunspots. And of course, these are concentrated magnetic field regions, we understand. If you look a little bit of close, then you could see that a sunspot, size of the sunspot is actually comparable with the size of the Earth. So you can imagine how big these structures are, how much energy and magnetic field they're confining. And if these energies are expelled from these closed regions, how much disturbances it can cause into the interplanetary space. So sunspots are actually magnetic structures. They emerge from beneath the surface. What we see on the sky on a white light image means our eyes also are sensitive to all visible wavelengths. And if I look at a standard older days film from the sun, these are all called white light images because they're composed of all these different optical wavelengths. You will notice that the sunspots are like this, but now we understand from our theoretical understanding and so on that these sunspots are probably connected by these magnetic field lines. They are called magnetic loops. And these magnetic loops are confining lots of plasma, but these sunspots are actually generated because these magnetic tubes are actually submerged from the beneath the surface. So here you see, I have gone underneath the surface of the sun. These are like magnetic tubes. You can compare with this, rubber tube. If you take a rubber tube and submerge it in a bucket of water, you notice that this rubber tube being slightly lighter than the water, it will try to, float. And then when it comes out of this surface, when it penetrates the surface, it forms a pairs of sunspots. So this is also again a very important aspect, that sunspots always comes in pair. One will be one polarity, the other will be the opposite polarity. So that is also a very important property of the magnetic field. So now these sunspots pairs, they come and they, sorry, I have to go back to the previous slide. They are coming from underneath, and then when they come out, they will form a magnetic loop kind of structure in the outside. And we see them lying there for a few days or several days. But then, because of this, some twist and so on, these tubes can get twisted, and then eventually that can get ejected as a storm. So these are called the solar storms. And this process, what Professor Choudhuri mentioned, is also called solar flares. And when such a flare happened, you saw a bulk of material was thrown into the interplanetary space, and then they will travel through this space in the form of a magnetic cloud and so on. So that's actually a shorter time scale behavior of a sunspot, how it is formed and how it emerges out of the surface and then can lead to a flare or a coronal mass ejection. When such a huge amount of mass is ejected or thrown into the corona, these features are called coronal mass ejections, and they travel into the interplanetary space. Now, I will actually step back a little bit, and I will now take it to a little bit of long-term study of the sun. In this plot, what I show is the yearly sunspot number for the last 400 years. Some days there are sunspots, some days there are no sunspots. There could be a period over which months or a half a year you may not find any sunspot. But in certain period, we'll find many sunspots in a day as well. So this alteration of solar activity, which is measured by the yearly sunspot number, is showing a kind of a sinusoidal variation with typically a 11-year of periodicity. And this is what is called the solar cycle. But if you notice, this solar cycle, these are called the amplitude of the cycle, is actually varying. And sometimes even the duration of these solar cycle can also vary between plus minus 1 year. Incidentally, this is the vertical two lines which is marked here. This was the period over which Samuel Swabe first systematically observed or recorded the sunspot number, and he discovered that there is a sinusoidal variation of sunspot number, and that's why the solar cycle is often named as Samuel Swabe as well. Where does we come now to India? From Kodaikanal Observatory, as it was already pointed out, which was established in 1899, from the beginning of the last century, regular observations of the sun exist, and not only from one particular wavelength, which is, as I mentioned, white light. You can also have different other filters. These are ionized, elements of, calcium, and here it's a hydrogen. And what it allows you to probe different atmospheric layers of the sun. Sun also has its own atmosphere, like Earth is had. There are some certain actually quite interesting aspects in the solar atmosphere is that solar atmosphere is actually hotter than the surface, which is quite unusual. I will, if I get time, I will briefly mention why it is so. But observationally, we know that corona, which is the outermost layer of the solar atmosphere, is much, much hotter than the surface, which is about 6,000 degrees, and the corona is at million degree Kelvin. So it is important to study different layers of the sun. This has been, realized more than 100 years back. And this is the one day, if I just go back into the archive, which is now, I was just mentioning, from Kodaikanal last 100 years, whatever observations have been taken, we have digitized all that data and put it in this archive. And then we can do really high quality science in this. We have calcium line spectroheliogram from all this period. We have white light data. We have H-alpha data. And we have some other, prominence objects, which are like a floating cloud in the atmosphere for all these periods. Why I'm mentioning this, again, this is it's a fantastic resource And this is also showing this concept of multi-wavelength astronomy existed more than 100 years back. And you can imagine when I'm talking about growth of solar physics in India, if you take back an observational aspect as well, at least, you can see what kind of resource Kodaikanal does provide today. And, some of my graduate students have worked. This is a new, sunspot area cycle. You could see the solar cycle, how precisely we are able to reproduce for more than 100 years. There is another property which is related to the solar cycle, which is shown in the lower panel. This is called the butterfly diagram, because sunspots do not appear actually at fixed latitude. Depending on the phases of the solar cycle, that means the beginning of the solar cycle, they will appear at higher latitude, and then with the progress of the solar cycle, they tend to move to the lower latitude. So these are properties which has to be explained by theoretical models, and that is what exactly Professor Raichuri and his students have been doing for last several decades, and we have made substantial progress in this. But again, I will not get into too much into that details, but I wanted to just again highlight that in the growth of solar astronomy, at least to the observational sciences, Kodaikanal Observatory has really contributed enormously. And we are only taking that legacy forward for the modern facilities. This is a slide which shows 4 images of the sun taken from different wavelengths. Earlier days, of course, from the ground-based, you can only measure primarily the optical wavelength. If you go to higher altitude, like in Ladakh region, or to some extent even in our location here at Devasthal, you will be able to see some amount of infrared as well. And infrared will allow you to probe a little higher atmosphere, namely the chromospheric heights of the sun. But if you really want to go even higher, atmosphere of the sun, you have to go to the space. So these are the images taken from 2 different space observatories of NASA. And you see many more structures and features, and you can study their dynamics much more detail. But my point is that today, for modern day solar physics, it is very important that we look at this in a comprehensive way. We just can't look at only the satellite data. We will miss the lower atmosphere. And if we just look at the ground-based data, we will only see the solar atmosphere in the lower heights, not the upper heights. Because now we understand the entire atmosphere is very much coupled. All these changes, whatever is happening either in lower atmosphere or in the upper atmosphere, they actually are responsible for all these dynamic events like flares or CMEs, which is happening in the sun. So it is important that we move into the multi-wavelength era. Here again, I'm showing some examples of multi-wavelength observations of active regions. As I mentioned earlier, these are the sunspots, if you see in the white light. And if you see them in coronal heights, you will see how these sunspots are connected by magnetic loop system, and how these loop systems also evolve with time. With this movie runs between few days. And these are chromospheric heights. They look slightly different. Coronal, they look much more extended loop structures. And of course, in the photosphere, you only see the foot points of these huge magnetic tubes. So that's a scenario which can be only obtained if you have multi-wavelength observation. So that's the active region. I'm again showing you one example of my students' work, which has been reported in Science a little while back. This is combining observation from ground-based and then space-based. So these observations are from space-based NASA's Solar Dynamic Observatory. These 3 layers represent dynamical changes in the lower chromosphere and in the photosphere, and associated changes in the magnetic field. As I indicated, now it is quite clear that the changes in the magnetic field, also the bipolarity, their interaction that leads to sometimes magnetic cancellations and so on. And that cancellation leads to certain form of dynamic jets. Here in this particular case, you see these are called spicules. They are jet-like features, and they are also responsible for the heating of the outer atmosphere, namely the corona. Because I just mentioned that the corona is much hotter than the photosphere, which is the visible surface of the sun. It was not easy to explain earlier that how is it that corona is much hotter. So some of these magnetic phenomena is responsible for heating in the outer atmosphere also, even in the quiet region. So I just thought, I will just show you certain, examples how the observational thing combining ground-based and the space-based is moving. So in my last 10 minutes, I will try to rush a little bit. And this is our projection of a national large telescope, a 2-meter class to be built in this beautiful lake called Pangong. Could see that we have certain small little observational facilities brought down here. Why NLST, the National Large Solar Telescope, is very important. Primarily the 3 big telescope which is now available are going to be available. One is in the Hawaii. This is in Big Bear Solar Observatory in US. This is in one of the Canary Islands. And there is a huge gap in the longitude which is required for solar observation. And NLST, the National Large Solar Telescope, which we are projecting to be built in the Himalayan side, will really be very crucial. This is just a comparison of the table. I will probably rush a little bit, where it shows that NLST is probably a world-class facility, can be of a modest size as compared to all the international facilities, but will be adequate enough to fill that gap. The other major facility from the space platform is going to be from our own ISRO's mission called Aditya L1. This is a multi-institutional mission. ISRO is, of course, funding and supporting us for all the different payloads to be built in different institutions across. And there are 7 payloads. There is a list of payloads here given. But for the sake of constraint of time, I will not describe all the payloads in details. But what I wanted to just highlight, it has a coronagraph which looks at the outer atmosphere of the sun, mimicking the total solar eclipse. Again, to mention that there are 3 visible and 1 infrared channel. Solar ultraviolet telescope is being built in Ayuka in Pune, which is going to look at the near UV wavelengths. Then we have particle detectors. 2 particle detectors built in different locations of ISRO, namely Physical Research Laboratory and Trivandrum and so on. We have 2 X-ray payloads, again built, one in ISRO and another one in Udaipur and combination of ISRO centers. And there is a magnetometer which measures the magnetic field of these particles which are coming from the sun, because we are going to be in the interplanetary space location called Lagrangian 1, which is in the sun-earth distance. And then anything coming from the sun towards the earth has to pass through this satellite. So we will have a combination of in situ instrument, which will detect the properties of these kind of mass and particles which are coming from the sun. And also we'll look at remotely to the sun and try to see its outer atmosphere in the form of coronagraphic images and near UV images and so on. And to be noted here again, we have a multi-wavelength aspect. This is X-ray, this is near UV, we have infrared and visible as well. So it's a suite of instrument which is shown here, how this payload will be at different locations in the satellite and so on. So this is expected to be launched next year, and we are all very much excited. So what we are going to do is, here it is the edge of the sun. Some disturbance comes from the sun. As I indicated, we will be primarily looking at this, layers of the sun. But why I am showing this movie is to highlight that it is still important to work with other agencies and international bodies to completely track these, ejecta, which is coming from the sun, and to track all the way to, near Earth environment. So sun is and Earth is actually almost like a coupled system now. If you really want to study Earth's, even environment, the macrospheric effects and so on and so forth, you have to understand what is happening in the sun in different time scales as well. So the corona, as I indicated, is highly variable. Here is an image from the corona from different eclipses. This is taken in 2016, 2008, 9, 10. As I can see, and they are taken in 2 different filters. And as you can see from the 2 different colored images, they are always, superposing on each other as well. So the complexity of these structures having different temperatures in the solar atmosphere or in the corona is also very well demonstrated here. And what is demonstrated here again is the solar cycle, that during the minimum period, the sun shows a different kind of structure as compared to an active period when you have more, activity and So to understand all these, we need to understand the physics of the magnetic field. And unfortunately, the physics of the magnetic field or direct observations are not easily available yet. So we need to have advancement in the models. And this is something which is also happening in SESI. My colleague Dipankar Nandi and his group has done some of these magnetic modeling. They predict actually how eclipse should look like before the eclipse day. This has been published, and they demonstrate that how good their models are. So we are going to use those models to predict or study the solar changes as well. So this is my last slide. Basically, I wanted to sort of demonstrate that really we are going into a huge changes, and there is a golden opportunities in the next decade. We need to actually look for these younger people. We had a solar physics, again, a workshop which Professor Arnab mentioned many years back in Kodaikanal. This time we had it in Leh, in Ladakh. And to me, the future of the solar physics in India is actually at their hand. And hopefully we'll be able to, guide them or motivate them towards taking it to the next level. Yeah. Thank you for your attention. Sorry, I have taken 5 minutes more than expected.
Okay, so thank you, Dipankar, for giving such an overview of solar physics in India in a very limited time. So I may mention that apart from the topics which Dipankar covered, there have been many other important developments which due to shortage of time he could not cover. So one very important development I can mention is helioseismology, the study of oscillations of the sun, which has given us quite a lot of information about the solar interior. And Professor Antia, who is in the audience, he played a very crucial role in making India is one of the major players in helioseismology. Anyway, maybe Vigyan Prasar will have a discussion of that in another talk. And now this floor is open for discussion. So as Dr. Kinkini Mishra pointed out that those who are attending it through this Zoom platform, they can either ask the question directly through Zoom or put it in the chat, and others also can put their questions in the chat. So any questions? So somebody who wants to ask the question orally can raise your hand or type it in the chat. Somebody who is in the Zoom.
Yeah, before answering, I must again, apologize or sort of compliment what you have said, that it is really, sort of difficult to cover many aspects of also theoretical aspect, particularly solar physics development. So I couldn't cover in that 30 minutes. I'm sure in future occasion we could address some of those questions as well.
Sir, we have received a few questions from our YouTube channel, and also some of the participants who registered at the time of registration also, they had posed some certain queries. So can I read them out, sir?
Yeah, sure. Please read them.
So the question which has been received from Shushant Rajoul, his question is, what initiative can we all take together for creating awareness about space science and technology among students and teachers in India, especially at grassroots level? How can we create easy sources of information about space science and technology to reach out to children?
Yeah, this is a very important aspect. Some of us are unfortunately engaged in too many things, so we can't distribute our time in appropriately. We have been actually discussing with the Astronomical Society of India on these regards as well. So how to have more training schools and workshop. I must admit that these even this picture what you see now here, these schools are dedicated for already graduate students, those who are already in the field. But what is important is to take it to the ground root level, as the person who have questioned. So we are planning to have more training level sort of workshops or schools. Incidentally, since the question has been asked, ARIES has been given the responsibility of Aditya User Center. So that means, Aditya is India's own space mission. How many, users we can generate from the younger side or from the university side is a very, very important aspect to be addressed. And I have been given this responsibility to conduct more regular sessions on basics on solar physics, what Aditya is all about, and if Aditya data comes, who all can participate in those analysis and so on. So please look at the ARIES website, and we will announce very shortly about very periodical training programs. Yeah. So we'll come up with that. Yeah.
Oh, thank you, Dr. Banerjee. I'll take another question, the second question. This is from the YouTube. Mohammed Nadil. Why does the duration of solar flares tend to be much shorter than the duration of type 2 solar radio bursts?
Okay, so these are slightly technical details because I have not told what is type 2 solar radio burst. So essentially the solar flares are now understood to be a process explained by magnetic reconnection. So magnetic reconnection is somewhat this movie in a more general sense I was showing about magnetic annihilation. Like, you have two opposite polarities, they are forced to come together, and then the magnetic energy gets converted into, kinetic energy and so on, and heat. So this process is very, very short. But whereas there are different type of radio bursts, and there are different phases of these, flares which we observe. So which phase of the solar flare is linked with the type 2 radio burst, that is what is important to be understood. Yeah. So they are not, representing the peak phase of the flare activity.
Okay. Thank you, sir. Another question is from Qazi Abul Firoz. When there is a solar eruption, is there any technique or code to determine the possible amount of energy released from the eruption?
Yeah, again, this is a very good question. Very nice. Of course, there are lots of theoretical development or theoretical work happening in this. So what is important is, as the question has been asked, can you sort of estimate how much energy will be released? That can be only understood if we know how much energy is in the first place there. So when these active regions are observed, they are composed of many sunspots, and their complexities are also important. I did not talk about the complexities within the sunspot. So one need to have a proper estimate about how much magnetic energy is stored in this, and it not necessarily that the entire magnetic energy which is stored will be entirely released. So one needs to also observe the ejecta which is coming from their volumetric estimates and other observational inputs. One probably have to get a better estimate how much energy is being carried. But if one assumes that entire energy of this active region is converted, then of course that provides an upper limit of how much energy these magnetic ejecta can carry.
Sir, another question from Veni Satyanarayana. Why can't we introduce the syllabi of space physics at undergraduate level? It may enhance interest over the subject and may lead to career in the astrophysics from hinterlands as well.
Yeah, it's a good question. There is always a
sir, I think
yeah, I also cannot see Dipankar, listen to Dipankar. He got frozen. Hopefully the connection will come back soon.
Yeah. We have two more questions on this from this platform, sir.
So I see a couple of questions posted in the chat for the Zoom. So anyway, let's hope that Dipankar will gain connection soon. Yeah. You are muted, Dipankar. Unmute.
Yeah.
Yeah. So what I was telling was that that early introduction of space sciences is debated. So when it is the most suitable for space science studies, once you have a reasonable knowledge about physics and mathematics, is something which is under consideration. And there are, of course, there are, ISST have a space science, program in Trivandrum, because ISRO wanted to inculcate, the space science early. And for ISRO's own particular applications and all that, they have introduced this institute called IISc. But in general graduation program or post-graduation program, how much we should, incorporate space sciences, this is something still, under consideration. But there are certain efforts, and we think that we will be able to incorporate, some elective courses, if not pure space sciences in masters.
Then we'll take 2 more questions, sir. This is from Shobhan Acharya. Can we launch citizen science projects so people can participate and also increase scientific temperament? It's more of, promotion, popularization, and outreach. These questions are more directed towards that.
Absolutely. No, it's a very important question. I am very much interested to do that. See, the citizen science program, this is very much supported by IAU also. There are lots of data available now. And the amount of data which is available, the professional astronomers may not be able to even ever, complete studying them. So I think it's a good idea to sort of, engage as many, citizens to these exercises. We are taking certain initiatives from ARIES. I'm planning to at least take it through certain universities and so on and so forth. Another thing is, some of the data what we have, that should be made to public. That's the first responsibility what we have. But again, data has to be processed and data has to be made public in a way or in a level where citizens can participate, actively. So I think this is a very important program. Again, as I mentioned, I have been connected with Astronomical Society of India as well. So we are taking up some of these, questions or suggestions very seriously. Hopefully, in coming years, you will see, direct, possibilities of that.
I think there is a comment from Professor Ananda Krishnan. Can you see it, sir? On the
I can just open the chat box.
In the chat box,
Yeah, so Professor
adding to it, yes.
Of course, whether it is a solar flare or coronal mass ejection, both are manifestation of the magnetic field of the sun. So this is, I think, a response to Yogesh. He posed a question in the chat box. And thanks to Professor Ananda Krishnan, he already answered that. So basically, the question was by Yogesh, is there a connection between solar flare and coronal mass ejection? Yes, there is almost a direct, connection. All solar flares almost leads to, coronal mass ejections, almost by default. But there are certain coronal mass ejections you may find because of some other instabilities, which may have a smaller flare, but it may not be a sort of big flare. Like prominences, these are the objects in the again chromosphere of the sun with a huge magnetic cloud, and because of certain instabilities, often they get exploded and ejected, and they lead to coronal mass ejection. But then why prominence do erupt? Also flare may have a role into play. So to be honest, there is a direct relationship between the flare and the coronal mass ejection. And as Professor Ananda Krishnan actually responded in the chat box, they are both manifestations of the magnetic field of the sun only.
So I see that there is another question which you can respond quickly. So what is the current status of mission Aditya?
So essentially, all the payloads are in its final stage of integration in the respective institution, and hopefully these payloads will be delivered to ISRO within next few months. And once these payloads are delivered to ISRO's integration satellite center, there all the payloads will undergo a lot of tests. These are called satellite fitness tests, you can say broadly, and then it will be ready for flying. So sometime next year, we expect to be in space. But of course, it will take a few months to reach the Lagrangian 1 point and so on.
Sir, Professor Pradeep Chakravarti has raised his hands. He would like to ask a question directly to you. Dr. Chakravarti, you can answer.
Yeah, he only posed this question in the chat box. Yeah, if he has
Okay.
an additional question, he can
Yes, yes,
unmute
okay.
and
Yeah,
ask.
yeah.
I don't see him unmuting. So there is another chat box, question in the chat box. Should I try to read and answer?
Yes, 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 sure, sir.
Okay. So Vidya Karak, he has asked this question. We are the future opportunities of students trained in solar physics. I mean the job opportunities. Oh, I see. So yeah, again, these are difficult questions. But my take would be that we should not train anybody in any branch of physics to a very limited way. My always suggestion is that even I do solar physics, I should be a physicist first, then I should be an astrophysicist, then I should be a solar physicist, so that I have a opportunity, or if I am asked to go and teach somewhere, I should be able to do that. So I think the solar physics training, fortunately, I think thanks to Professor Arnab Choudhuri or Professor Antya and Ananta Krishnan, they have trained us to some extent to have this, little bit of flexibility. And I think it's our responsibility to ensure that the solar physicists or solar physics students are also trained in that way. But having said that, when you see such major facilities which are coming up in next decades, whether it is Aditya L1 or NLST, India never had any facility of that scale. I mean, not even 20% of that scale. Primarily, the solar physics was focused mostly on the theoretical aspect and data from other space missions from NASA. I must be very open on this. Some of us also got completely matured only because of this open data policy of the NASA mission. So this is also another aspect I think we have to keep in mind. All the future facilities should have provisions for inclusiveness, trying to have as many people as users to widen the scope. And then I think there are many such things. I did not talk about one element is the industry partnership, how much technology which is involved in these kind of missions, how much engineers are involved in this. I didn't get that opportunity, but since the question is asked, it is actually solar physics shows the way. When you want to build a telescope, it is important that you have lots of technological involvement from engineering side, from technical side, from computation. We are dealing with big data. So, AI ML is the, key thing for us for today to do, handle all this large volume of data. So I think there is lots of scope in that aspect as well. Participating in this, from the technical qualified students, and subsequently, once they are involved in this kind of programs, they can go to work in the industry as well, because they are industry ready for this, industry demand. So I think that. I mean, I am quite hopeful about the future of job opportunities as well.
So about this job opportunities, maybe I also can make a comment. So it was about 35 years ago when I was in US and I planned to return to India from US, and I was looking for jobs. At that time, there were barely 4 or 5 places in India where I could apply for jobs, and I knew that an application from an astrophysicist would be considered, because at that time there are these 5 IITs, and most of the IITs and most of the universities had the impression that astrophysics, maybe not really physics, so most of the physics department would not look at the application from an astrophysicist. And we solar physicists had a double difficulty. When places which would be interested in astrophysics may think that, oh, maybe cosmology is the only astrophysics. So the scenario has changed tremendously during the 35 years. And I suppose one has to give quite a lot of credit to Professor Narlikar, who established AYUCA to spread awareness of astrophysics within the Indian university sector. And now many of the IITs, including the older IITs, which did not have astrophysics groups for many decades, now they have astrophysicists, and new IITs and ISARs, they also have astrophysics groups, and in many of the group there are solar physicists. So I would say that the job opportunity of solar physics is now quite good. Of course, you have to be do very good work. A young person has to be very good work and has to be internationally competitive. If you just do mediocre work, you may not be able to get a job. But for, I think, the young person who is now able to do internationally competitive research in solar physics, I think is able to get jobs in India. Okay, so I think we had enough discussion. So now over to you, Dr. Kinkini.
Yeah, is there any, there's some comment on the chat box?
Yeah, should I just address that?
Yeah.
So there is a question, how important do you think the Hisako Koama's observation regarding to the sunspot? In fact, very important. Basically, the point is that the sunspots have been observed over more than a century from different parts of the globe. I today mentioned only about the Kodaikanal, but there is a Mount Wilson, which has contributed enormously. There are quite a few observatories from Europe and again from Japan. They have done these early observations. They're sometimes in the form of drawings, not always in the form of direct imaging and so on. So what is important is to collect all these informations from different observatories and then make a composite series. In fact, the one which I showed, one of my students who has done this new sunspot area series, take the data taking from 13 different observatories. So we do now today cross calibration against these kind of time series observations from different places, and then we try to put all of them in the same place, because if one particular place, if there is a problem, that gets sort of corrected by combining data from a number of different places. Also, the fact is, historically, I mean, there are certain days you will not have observation from one particular ground station. So typically you will have 250 to maximum 270 days of observations. You will miss at least 70 days of observation. So that 70 days of observation can be taken from somewhere else. So that's how we do it. So since you mentioned, so I don't recall actually all the details of these particular observations you are referring to, but it is worthy to mention that in Japan there are quite a few observatories where we are actually leaking data, and we have joined a program also from under this Indo-Japan program of DST, where we are actually currently looking at that data as well.
Right. So no more questions for today. And in case there are any further questions, you can share it with us at the ISTI portal, and we will pass them on to Professor Dipankar Banerjee as well as to Professor Arnab Choudhuri, and those questions will be answered. So sir, we are very thankful to you for taking to this beautiful cosmic journey and making our audience understand why the study of sun, our nearest star, is important. And your lecture has provided us with a more scientific vision to view sun just not as a life-supporting star. And the multi-wave lens that you have provided our audience with will ignite their curiosities and motivate them to take up solar physics or astrophysics as their core career options. And your lecture has provided a thorough information on the measurement of various dimensions of sun. I, on behalf of Vigyan Prasar and on my own behalf, thank Professor Arnab Choudhuri and Professor Dipankar Banerjee and express my sincere gratitude to you for joining us and driving us through the journey of growth of solar physics from ground to space-based platforms. And I would also like to take this opportunity to place on record and hearty thanks to Professor Sachin Chaturvedi, Director General of RIS, Research and Information Systems for Developing Countries, and Dr. Amit Kumar from RIS for their enormous cooperation, ideation in organizing this series of lectures, which we are organizing every month. My special thanks to all the participants and attendees, without whom this session holds no value. Finally, I extend my thanks to our director, Dr. Nakul Parashar, for addressing the session, as well as for supporting and motivating us throughout. And I would like to also acknowledge the efforts put up by the entire team of ISTI Portal for the perfect logistic support from behind. For more information about the upcoming webinars and India's efforts in science and technology, I would request all of you to kindly visit India Science, Technology and Innovation Portal. Thank you so much. Thank you one and all for your kind